I will resume now with a presentation from Tim. Tim is a machine learning researcher focusing currently on research on the area of binary neural networks at Plumerai in London. Prior to this, he was a PhD candidate at the Delft University of Technology, where he worked on deep reinforcement learning for robotics. His research work was published in major journals and conferences such as GMLR, ICRA, IRIS, or NeoRIBS. Tim, if you want to go ahead, please, whenever you're ready.
Thanks very much. Let me share my screen. There we go. So yeah, thanks very much for having me. It's been a really great workshop so far. I've very much enjoyed seeing all the talks. I want to take this talk in a slightly different direction though. So far, all the talks have mostly been around how do we get more accuracy out of extremely quantized networks, or how do we keep the accuracy the same while we make the inference much faster or much more efficient? And I want to ask a slightly different question, which is actually accuracy actually enough to look at? Like what aspects of BNN performance do we miss if we just focus on accuracy? Because there are some ways in which if we make a binarized neural network, maybe we make the same amount of mistakes on our test set, but we make different mistakes. And binarization or designing networks for binarization might impact which kind of mistakes we make. And we might miss that if we just look at accuracy. And we've kind of learned this at Plumerai in our journey from doing more fundamental machine learning research at our start towards making actual useful BNN products for the real world. So I want to share a bit of that with you. So let me start with, excuse me. Let me try that again. Yeah, there we go. So let me start with a bit of our history. So as I mentioned, we started out doing quite fundamental research. So for example, initially we looked at how do we train binary neural networks from scratch. And so at NeurIPS in 2019, we came up with this paper on our binary optimizer method, which it was great to see at least two presentations previously that this one was mentioned. And of course, because we do computer vision research, as everyone mostly does, we tested our results on ImageNet and we compared our method to other optimizers for some popular networks. And after this last year, we looked at inference and we designed our own inference engines to run binary neural networks very quickly. And we used this to show that if you want to actually get really efficient inference, you can't just look at theoretical measures like the number of operations in a network, but you actually have to implement it on device and see where the bottlenecks are and then optimize for that. And so we did this and we made a network called QuickNet, which for the same inference time got higher accuracy, again, on ImageNet than competing networks. Besides our research, we also share some of our code. So for example, we have the LARC library, which is a library which extends TensorFlow and Keras and makes it easy to do BNN research. We have the LARC compute engine that I just mentioned, which makes it easy to deploy BNNs on Cortex-A devices like the Raspberry Pi or Android smartphones. And we have the LARC Zoo, which is a collection of trained networks, both our own and those from the literature, that have been pre-trained on ImageNet and can just be easily deployed. So if you're interested in any of this, make sure to check out larc.dev. But while getting like a good score on ImageNet is obviously nice, it's not really the point of our company. The point of our company is that we want to make actually useful products for the real world. And the lesson we had to learn is actually that what we do on ImageNet doesn't always transfer to the real world. So for example, one domain where we think that BNNs are really have a lot of potential is for TinyML. So this is like tiny little chips in very cheap applications where there are very severe resource constraints. So very small amount of memory, slow processor, but many of them all over the world. So here we really see a potential for BNNs, of course, because of the really efficient inference. So for example, one task that we do in this TinyML space is person presence detection, where we take an image and we just want to say, is there a person there or is there no person in the image? And another task is person detection, which is basically the same thing, but we also ask where is the person and we draw a bounding box. So we've been developing BNNs for this and training them and running them on these tiny little MCUs. And this has gone well enough that we actually did a live demo of this on the TinyML Summit earlier this year. And as you can see, even on like these tiny devices, BNNs can definitely solve this task and can do it very well. But as I hinted at earlier, we had to learn some tricky lessons in going from ImageNet research to making these actual real world products. And mostly these lessons were that some of the methods that we develop for ImageNet, they just do not really work when we try to make a product like this. And we really learned that it's very important to not just optimize for the right task with the right data, but also to look at the right metrics in order to know whether we're actually making progress towards better BNNs. So just to give you an example of something that works in ImageNet that did not work in this TinyML space, knowledge distillation worked really well on ImageNet. We tried it. We tried some methods from other people. They worked really great, got several percent ImageNet accuracy, but they really work really great on ImageNet because there's 1,000 classes and a lot of them are dogs, and we can learn that all of these dogs have some correlations and we can transfer that to a student, and it's great. But now if we go to this, for example, this visual wake words task of person, no person, we only have 2 classes and they're mutually exclusive. So this just does not transfer and we didn't see any gains there. And so there's 2 papers mentioned on the slides that also make claims like this. We're definitely not the first one to realize this, but really the benchmark that we optimize for, like ImageNet, that selects from methods. So some methods will work on ImageNet, some methods will not work on ImageNet. And it's a little arbitrary because the methods that don't work on ImageNet might work really great on another domain, like in this TinyML space, and vice versa. So let me look at a task and a data set that is relevant, where we see BNNs being especially relevant right now, so in this TinyML space. So we have the visual wake words data set from Chowdhury et al. From 2019, which is basically this task, and it's a public data set, so that's great. So it's person versus not a person in an image. So this is an image from the paper, and it describes basically exactly what we want because we're interested in making some products that work indoors. So on the left, we have an indoor scene with people. On the right, we have an indoor scene without people, and this is great. Now, if we look at the actual data set, it's a little bit different because the visual wake words data set is actually a subset of Coco, and Coco in itself is sourced from Flickr. So these are all images that are taken by people for the enjoyment of people, and they're not really for machine learning, but they've been scraped into a data set, and then we try to do some machine learning on them. Okay, but at least we have data that's relevant for the task that we're trying to learn. So then the obvious thing to optimize for is accuracy. How many mistakes do we make? So the first obvious problem with optimizing for accuracy on this specific data set is that, as I mentioned, all of the data initially comes from Flickr. So that means that, yes, we have a training set and we have a validation set. But if we train on this training set and then we validate on this validation set, they both contain kind of the same sampling biases that stem from the fact that these are not images for machine learning applications. These are images that are, well, why do you take an image? Because it's interesting or beautiful and not because it accurately represents a real world distribution. So the first question that we want to ask is, if we train on this visual wake words training set and we validate on the validation set, does this accuracy on the validation set actually predict how we do in the real world? So to answer that question, we've collected a lot of real world data using TinyML cameras. So these are very cheap cameras that have lots of issues. So we have this more realistic data, and then we want to know, how do we do on that? And can we predict how well we do from our validation score on this public data set? So in order to answer that question, I will introduce two networks to you. So the first one is a very shrunk down version of the QuickNet I mentioned earlier that we had developed using our inference stack on ImageNet. So it kind of stems originally from ResNet. It has some improvements from BiRealNet and then some of our own improvements on top. But you can kind of think of it as a ResNet derivative. Now in these slides, I will, for these blue parts in the networks, I will consider 4 variants. So the first is that we don't binarize these blue parts, which on these MCUs means we leave them in 8-bit. The second thing I'll consider is that we binarize only the activations to get a binary activation network. The third thing is that we binarize just the weights to get a binary weight network. And the fourth thing is that we actually go full by BNN and we binarize both weights and activations of these blue parts of the network. So if we do this and we test this network on Cortex-M, we see that we get a good speed up from binarizing parts of the network, and we get a very significant reduction in the amount of memory that it uses. Now, because this is Cortex-M, there's no pop count instruction on Cortex-M. So we could even on other chips get a much bigger speed up in inference time, but this is already nice. Now I'll introduce a second network. And the reason I'll introduce a second network is that I'll show a bit later on that the network architecture, not the fact whether we binarize it or not, but the actual architecture matters a lot in what kind of mistakes we make. So this is SpiderNet, and the idea behind SpiderNet is that BNN training can be difficult because of our gradients that go through the activation quantizers. They can get a bit scrambled. So here we have lots of shortcuts so that we can bypass parts of the network and the gradients can still freely flow. And we keep the memory of these shortcuts limited by doing basically a global average pooling on them. So the shortcuts on the left are quite memory friendly. And we see here again that the non-binarized version is a lot slower than the binarized version, which runs in about half a second on this chip. And we save a lot of memory by binarizing these blue parts. Okay, but so the question was, can we, from the accuracy on this visual wake words data set, predict how well we do in the real world or on our collected test data? And if we look at SpiderNet, then we do indeed see a fairly good correlation, as in if we make a big step in accuracy on the visual wake words data set, then we also make a significant step in real world performance. But if we now add QuickNet to the mix, then we see that whether or not we binarize QuickNet, even though binarizing QuickNet obviously gives us large savings in inference time and amount of memory, it doesn't really show much of a difference on the visual wake words data set. And even though there's still a big spread in real world performance, we can't really predict a real world performance from the validation set accuracy. So how do we then make our BNNs any better if we can't predict their real world performance? So the way we do this is that we basically go through this cycle a lot of we train our models, and then we perform all kinds of analyses on them. We take them out in the real world and we test them. We test them on data sets. We use all kinds of tests. And we basically identify when they fail. And then for those specific scenarios that we've identified where they fail, we collect more data. Then we retrain our models. We test it against not just this new data we've tested, but all previous failure cases. And we make sure that we improve and we keep improving and we keep going through this cycle. So if this kinds of development of machine learning models is interesting, then I can also highly recommend Andrej Karpathy's talk from earlier this CVPR, where he basically explains how this is done at Tesla. But okay, I can definitely see how anyone from academia might now be thinking, well, that's all nice, but obviously we need a fixed data set so we can compare to everyone else. And yeah, agreed. But there's still questions even on a fixed data set that we can ask beyond just accuracy. And specifically, we can not just ask how many mistakes we make, but we can ask when we make those mistakes. And I want to specifically focus on two things, bias and robustness. And I also want to mention some great work from Sarah Hooker, which also shows that when we do model compression techniques like quantization and pruning, that even though we can sometimes get the same accuracy, the cases on which we make mistakes can definitely shift a lot. So let's first look at bias here. And the way I'm going to look at this is that we take the last part of our network. So in the very end, we have person versus not person. But then the layer before that, we get an activation network of some activation vector, of some size. And we're going to look at that. We're going to first reduce its dimensionality with some dimensionality reduction technique. And then we're going to see whether the individual dimensions in this reduced space have some semantic meaning. And it turns out that they do. And the way we can see this is that if we take all our training data and we basically sort it by how much they activate these individual dimensions, then we get specific concepts. So even though we just train on person versus not person, we might be able to learn a concept like food. So if we do this for SpiderNet and we look at what kind of activations, what kind of concepts it learns, then we see things like that it learns very primal colors, like it sorts all the green colors together or all the white colors together. And this might be because of all these shortcuts, which we just put in there because we thought it would be good for gradients. It might have very direct access to like these first layer features, which might focus more on colors. If we look at a non-binarized version of SpiderNet, it has a significantly different accuracy. But if we look at the concepts it learns, it actually learns very similar concepts. So the concepts here seem to be very much related to the architecture and not to what accuracy it gets. Especially if we compare this to QuickNet, where QuickNet learns maybe because it's a more traditional network where we keep on making changes to our intermediate activations, it learns maybe a bit more advanced concepts like leaves or windows or things like this, or pillars. And we see again that the binarized version versus the non-binarized version, in this case, they have quite similar accuracy to the non-binarized SpiderNet, but they both learn the same thing. It doesn't depend on binarization, it depends on the network architecture. So let me show another way to look at this. So we have our visual wake words data set, and let's say we need to classify this image. So this is an image of people on a platform of a train station, and it happens to be a black and white image because, again, visual wake words data set comes from Flickr originally. So these are things have been done to these images because people thought it was pretty. This image might be hard to classify because it might be difficult to see these people because they're quite small and yeah, they're black and white. But there's this well-known concept in machine learning of shortcut learning, where if it's hard to learn something the way we've intended it, a network might still find another way to learn this, to classify these images. So for example, a sampling bias that is in Flickr is that people are more likely to make black and white portraits of people than they are to make black and white pictures of other things that aren't people. So we can learn this correlation of if an image is black and white, it contains people. Now, of course, if we test that on real world data, that does not generalize because this is just a coincidence on the training data set. It's not a real thing. So we have a method where we can basically find these images that encode some correlation that does not generalize to our own test data. And if we do this for the SpiderNets and the QuickNet, then we see again that both of the SpiderNets learn very similar things. So both of them are sensitive to these black and white images where they might learn that black and white means person. Whereas if we look at the quick nets, both of them, regardless of binarization, learn this trend that does not generalize of small people outside. And the reason this does not generalize is that all of our test data is inside. But again, if we just look at accuracy, then we might not pick up on the fact that these networks learn different things and different shortcuts. So if we just sort these by accuracies, we have three of them on a heap, and the other one is quite separate, even though the kind of mistakes they might make is more dependent on the network architecture. So let's look at one more example where accuracy might really hide other aspects of performance that can be quite harmful. So here we have the 8 networks that we've considered so far, and they're sorted by their validation accuracy on the visual wake words dataset. And now we're going to test them on another dataset, namely the celeb set from Raji et al. And this dataset contains crops of faces of people, which is a subset of the problem that we've trained for. So we might expect to generalize to this problem. And indeed, if we look at the accuracy on this dataset, we see that the better the accuracy on the visual wake words dataset, the better the accuracy on this celeb set. And we might think that as we get better accuracy, we're actually doing better. But what this hides is the fact that if we just train on the visual wake words dataset, which I should mention we don't do for our actual products, but if we just do this, which I did for this presentation, then we make more mistakes on people with dark skin versus people with light skin. And the amount of mistakes we make on people with dark skin, this gets worse as the accuracy improves. So again, if we just look at accuracy, we might think we're doing better, while in fact we're not doing better. So a lot of this has been quite general, or at least like second order effect. We might create some network architecture because we think it's good to binarize, and then if we only look at accuracy, we might miss things that are relevant. But let me finish with something that is actually quite specific to binarization, or at least it's, binarization has a strong influence on this, which is robustness. So this is just the fact of we have an image, we make a prediction. If we now make a very small change to the image, how does the prediction change? For a good product, a product that people would have confidence in, the prediction would not change much because visually the image hasn't changed. But of course, we know that neural networks can be very sensitive to small changes in the image. And what I'm going to look at here is, does that sensitivity change with respect to non-binarized networks if we binarize parts of the network? So here's SpiderNet again. And so we look for several kinds of changes to the input image, very subtle changes. How sensitive are these networks? How sensitive are the predictions to these changes? And what we see is that if we binarize weights, then across the boards, we get slightly less sensitive to changes in the inputs. But if we binarize activations, we get a lot more sensitive to changes in the input. And again, if you look at the accuracies on the visual wake words dataset on the bottom left, then binarizing weights and binarizing activations has very similar effects on accuracies. So even though we make the same mistakes or the same amount of mistakes, the kind of mistakes that we make change. And some mistakes are definitely worse than others. Now, this is definitely a solvable problem because if we, for example, look at the QuickNet architecture, then we see that the sensitivity is a lot lower. So all of these are very much solvable problems, but we can obviously only solve them if we measure for them in the first place. So to conclude, we really believe BNNs are great in general, but especially now for the TinyML space where there's very resource constrained inference. And yeah, these benefits of like increased inference speed, reduced memory size, reduced energy, they can really enable new applications in the space that are without BNNs infeasible. But BNNs can still be made better, but we can only make them better if we can properly assess their performance. So specifically what we found is that methods that work on ImageNet don't necessarily translate to this TinyML problem, to these TinyML problems. And yeah, just these somewhat arbitrary computer vision benchmarks are not always relevant and sometimes filter out methods that might be better in other domains. And the second thing I looked at was, is it enough to just ask how many mistakes we make? Or should we also, when we do things like introduce new networks or binarize things, should we look beyond accuracy and look at things like bias and robustness in order to make BNNs actually much better? So if any of this has sounded interesting to you, then we are very much happy to collaborate on some of this research. And please feel free to reach out through one of these email addresses or have a look at the website. And with that, thank you very much again for inviting me to speak here. And I'm happy to take any questions.
Thanks for the great talk, Tim. It's really good to have also more industry perspective, I guess. Does anyone have any questions for our team? If no, I'll go ahead with one. So I was wondering, finding models that, let's say, work well on this on these more real data sets, and finding some better architecture or methods, let's say, do these methods translate when you test them back to ImageNet, for example, or is this a one-way street?
So we haven't yet tried the other way around of developing for TinyML and then going back to ImageNet. I do think when methods do generalize between TinyML and ImageNet, it makes a lot of sense to do research in TinyML, if even just for the reason that a TinyML training run can take hours, whereas an ImageNet run can take days. So you can just do research much faster. But I do think that, so if we take the visual wake words data set, for example, that will also filter out some methods that might have worked on ImageNet but don't work there, and vice versa. So I do think we need to, test on the benchmarks that are relevant to where we think the applications are.
Thank you. Do you think if let's say that we don't necessarily have enough data for that particular problem that we're trying to solve, do you think you can get away with this by testing on multiple data sets and hoping that if a model is consistently better on multiple data sets, which may have some bias, but different type of bias, hopefully, we could get a model that is also more suitable really for the problem at hand? Or do you think we really need the data and there's no way to get away from this?
I think multiple data sets is definitely better than just the one. I think the ultimate thing is having the right data and collecting actual data from the devices that you're going to test on. But multiple data sets is better than just the one. But with the caveat that it is then good to see that they don't have the same sampling biases. So for example, if we substitute our visual wake words data set data with open images data, then they still both come from Flickr. So we might still have the same biases in there. So yeah, diversity definitely also better, but there should actually be diversity.
Thank you. I think we have also a question from someone from audience. Right, so I'm going to read it if that's okay. So thanks for your nice talk. Do you believe this alternative metric like bias and robustness can have some negative correlation with the conventional accuracy, or all of them can be improved simultaneously?
That's a good question. I think definitely if we don't make mistakes, then we're also not sensitive to bias or robustness because so in the end, if we don't make a mistake, if our accuracy is 100, then we don't make mistakes anyway. So it's also not interesting which mistakes we make because we don't make mistakes. So I definitely think in the end, if we could get to that point, then they're all in alignment. But if we can't get to that point, I do think they can be opposite. I do think it can sometimes be better to make slightly more mistakes if they're better distributed. Like if we make mistakes that people who use the product can live with, that's okay. But if they're mistakes that you can't live with, then that's obviously a no-go.
Great. Thanks again. Thanks once more, Tim, for your great presentation.
Thank you for having me.